Okay, so here we are on our last day. Actually, I want to start by giving a little bit of a summary and just to let you guys know about this course compared to other courses, because this course is kind of unique. And so I think maybe, you know, if you go on and go to school somewhere else, it might be good for you to know how this course differs from most courses, most data structures courses. And also, I'd like to give an acknowledgement to some authors of another book that has influenced this course. Now, first of all, we have done this. You know, I've told you this one over and over again, right? This is the Gang of Four: Design Patterns, Elements of Reusable Object-Oriented Software. And this book was very influential in the design of this course. And I also need to acknowledge that my colleague at Rice University, Zung Nguyen, is the one who's the mastermind behind the way this whole course is run. So you know what I'm going to ask next. What are the three goals of this course?
Data structures.
Okay, so first is data structures, second is object-oriented programming, and then C++. So now the title of the course is Data Structures, but it is really unusual to merge object-oriented design patterns into a course in data structures. And so this is very unique. So you should probably know, you might need to know, or you probably should know, that normally data structures courses are not taught this way. Because, and I don't know if you realized it, but here near the end we were more concentrating on the data structures themselves. We finally got to the topic of data structures. You know, like for example, what is the data structure of a graph? How can you represent a graph? And then the algorithms that come out of that representation of the object. And so this book that we've referred to a lot is the basis of the object-oriented design patterns that we use in this course. But I also want to point out another book that we used to use in this course a lot. The reason I'm pointing this one out is because this is kind of like the Bible. This is a very well-known, widely used. If you go to grad school, I can almost guarantee you with 99% accuracy that if you go to grad school, you'll use this book. It's called Introduction to Algorithms. It's in its third edition now. It used to have just three authors, Corman, Leeserson, and Rivest, and it was known as CL and R. And so everybody knew this. Just so you know, that was the Gang of Four. This was CL and R after the authors. And it is encyclopedic. And it covers, in this course we have used some of the algorithms in this book, but only maybe about 10% of it. You know, it's encyclopedic, and it has many different data structures, but mainly the algorithms that are used to manipulate those data structures in it. And I have had, the reason I want to just present it here at the last is because I have had many times over the years, students have come back, alums of the computer science program here, who have gone to graduate school, who have gone to industry, and they still have this book on their shelves, and they still refer to it, and it's just extremely useful in any kind of a professional coding environment to be able to have that as a reference book. And I will also say that one of the reasons that motivates me to do this is because these algorithms that we have done on the implementation of a graph and a digraph, and the breadth first and the depth first and the gray and the white and all that kind of stuff, all those algorithms were taken from this book but modified to fit our object-oriented design pattern stuff. So for example, they would not talk about iterators in there. See, but it would just be, and another nice thing about this book, about Introduction to Algorithms, is that it is language independent. They use a pseudocode in there. The pseudocode is quite different from the pseudocode that we're using, and so our pseudocode is more closely matches C++. Their pseudocode is a little bit more abstract, but it's language independent, and so it's not tied to any language, and therefore, you know, you can look up algorithms and get the logic from the pseudocode and then translate it to whatever language you're working in if you need a particular implementation of a data structure and an algorithm to manipulate that data structure. Okay? So anyway, I just thought it's good to know the literature in some of these works. In the history of the way this course evolved was there used to be this idea of combining data structures and algorithms and object-oriented programming and software engineering has been presented before at various venues, and it's very hard. It's a very hard sell because people see what the typical reaction is. People see, well, why do you make it so complicated? A linked list is just, you just have pointers in a node and boom. Why do you have to have all this big stuff? You know, it's in a way we're making it more complicated. Do you see what I mean? Than just a simple, why have all these iterators? Why not just program up a little linked list? But the idea, the philosophy behind it is that as long as you're going to be doing programming and as long as you're going to be implementing data structures, why not do it in an environment that is software engineering sound? In other words, why not do it why not work with software the way the software is provided to you in the industry with a library? Do you see what I mean? Instead of just having, course exercises with sloppy throwaway code, why not learn to implement preconditions, and why not have everything documented, and why not have it so that we develop good habits in coding? You see what I mean? So that's one of the reasons that I like this approach of combining object-oriented design patterns with data structures. Anyway, that's my little spiel. Okay. So what I would like to do this time is just review some of the theory stuff. And I think it all started in chapter 3. So here, can we do this? Can you remember how to do this? Here is, let's review figure 3.4. This is do you remember how to do statement execution counts? You don't like them? Yeah, well, I mean, that's where it all starts. Nested loops are big theta of n squared, but where did the n squared come from? You got to be able to count the statements, right? Okay, so here, let's just do one. This is selection sort, and here's the code. For int k gets length k less than 1, k minus minus. So what happens if length is 2? How many times does line 3 execute? Well, if length is 2, what are the values of k? Yes. K greater than 1, just 2. Are you with me? But the test, but the extra test with 1 makes it execute twice. Is everybody with me? And then what about line 4? Can you anticipate that one?
1.
Yes, that's 1 less. So that would be 1. And then what about line 5? Now this is j going from what to what?
From 1 to k.
Well, 1 to k. So the value of k is what?
2.
2. So for int j gets, because there's a test at the end of this one too, right?
That's the fit. Oh, yeah.
Okay. So twice. And now how about the if? 1. Yeah, 1 less. And now how about, we're doing best case, so the body of the if?
0 times?
0, because we're doing best case. And now what about the last 3? Once, once, once. So total, you add those up, you get 9. Now what about if length is 3? If len is 3?
For loop executes 4 times.
So
the for loop executes 4.
line 3 executes.
4.
Oh, we have a difference of opinion here. Good thing we're reviewing this.
3.
Now do we agree that it's 3?
Yeah.
Okay, and now what about line 4?
2.
2, and then line 5?
2 plus 3.
Yeah, this time it's 2 plus 3. 2 the first time through, and 3 the next time through. Remember that? How that works? So, yeah, and then what about line 6? 1 plus 2, and line 7,
0.
0, and line 8, sorry, line 10.
No.
It's not, it's in the outer loop, it's not in the inner loop. Yeah. 2, 2, 2. And then you add those, that's 19. Okay, so now let's do it in general. So that was 2, 3, otherwise it would be, the next one, if for length equals 3, what would those numbers be? Let's do for length equals 3 just verbally. What would it be? 4, 3, 2 plus 3 plus 4, 1 plus 2 plus 3, 0, 3, 3, 3. So now what is it for n? N. N minus 1. Are we good? And then what?
2 plus 3 plus dot 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 dot.
Plus, what's the last one? Plus n. 2 plus 3 plus dot 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 plus n. And what was the next one? 1 plus 2 plus dot 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 plus the last one is n minus 1. And then 0. And then what is what are these?
N minus 1.
n minus 1, n minus 1, n minus 1. Now, do you remember how to compute those summations? What's the sum on I, 1 less than or equal to n, less than or equal to I? Sorry, what's the sum on I, 1 less than or equal to I, less than or equal to n, body I? In other words, what is 1 plus 2 plus 3 plus dot 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 plus n? That's the one we have to remember to know. Remember that? No.
That's like n plus 4.
N times n minus 4?
Minus or plus?
Plus.
I think it is plus. N times n plus 1 over 2. This you need to know. And from this you can calculate the other summations, right? Because that first, that 2, what is the 2 plus 3 plus dot 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 plus n? That's this whole one minus what? Minus 1, I think, right? So 2 plus 3 plus dot 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 is all that whole thing minus 1. And what about the 1 plus 2 plus dot 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 plus n minus 1?
Oh, it's just n squared over 2.
Well, it's the same as if it's the same as the one that it's the same as our standard formula, but the last one is n minus 1. So it's the same as the standard formula, but it's with n replaced by n minus 1. So what is it? N minus 1 times n over 2, right? So that's 1/2 n squared minus 1/2 n minus 1. All right, so anyway, those are good. Yeah, so anyway, that's how that works. And then best case, or worst case is different, okay? So the conclusion is that the execution time is quadratic in n. All right, so that was one nice little review of statement execution counts. No guarantees, I'm just saying. Then we did asymptotic analysis, so which is better, f dot n is 25n plus 93, or f dot n is 2n squared plus 4n minus 3? The answer is, it depends on the value of n, right? Because there's a crossover point. But for big N, which is better?
25.
Yeah, 25n plus 93. And now, now you remember how to prove something is big O? Big O means what? Upper bound. All right, so there exists a what? To show that f of n is big O of g of n, what do you have to show? There exists what exists? Constants CNN not, positive constants CNN not, such that f of n is less than or equal to what? C times g of n, right? For all n greater than or equal to what? And not. So one of those two constants. Yeah. Oh, now let's remember big omega. So now what is big omega? So f of n is big omega of g of n if what? Constants c and n not, such that f of n is what? Well, f of n is greater than or equal to constant times g of n. So the constant, so that's a lower bound, right? And then we did some examples of that. Here, let's do this one. Let's do n cubed minus 5n is big omega of n cubed. So what do we have to show? There exist positive constants, C and n naught.
Such that f of n is
So, but what is our f of n? Such that what?
n cubed
Minus 5n is what?
greater than or equal to
Well, now which is it? Less than or equal to what? C times n cubed for all n what? Greater than or equal to n naught. Remember that? So here, so how do we do that? What do we start with?
Show that there exist two positive constants.
Oh yeah, we have to say it. So must prove that there exists positive constants C and n naught such that n cubed minus 5n is greater than or equal to C n cubed for n greater than or equal to n naught. So you need to be able to write that down. Okay, and now what? Oh, this is a little bit of a review. Yeah, prove it. How do you prove it? What do we start with?
5 or 3.
Yeah, left-hand side, I think, right? So n cubed minus 5n. So we start, so n cubed minus 5n. But now, can we just drop, we want this to be what? Greater than or equal to something. So can we just drop the minus, the negative, can we eliminate a negative value, yes or no?
Yes.
Wait a minute. Can we? Can you just drop the negative 5? Can you say n cubed minus 5n is greater than or equal to n cubed?
Yes.
How can this be greater than or equal to this? If you're dropping, if you're dropping this? Oh, we got to think this through.
So are we going to increase the negative? Increase
Well, but if you increase the negative, you're going to,
Do you have to do that trick where you like
yes, there's a trick.
side of the
Yes, there's a trick inside. You have to do that computation inside of the hint.
n cubed minus
Because,
is greater than
now what is the technique? We'll call it a technique instead of a trick. So what was that technique?
you said that greater than or equal to 0, and then you solve for
Well, but what is it greater than or equal to? Now here's the thing. Let's remember this. What about C and n naught? They both have to be what?
Positive.
Positive. But it is allowable for C to be what? It has to be positive, but it's allowable for it to be what? No, it can't be 0. It can't. Yes, it can be less than 1. Are you with me? The constant has to be positive, but it's allowable for it to be less than 1. So what we can do is we can just pick it to be what? What was the technique? 1/2, I think, right? We can claim that this is greater than or equal to 0.5 n cubed. Do you remember this technique? We can claim that this is greater than or equal to this.
Why do we choose like 5?
Well, if we chose like 0.8, we would get a different C and a different n naught. But as all we have to do is show that a pair exists. Yeah, are you with? So you pick. In fact, a lot of these things, there's not one particular C and n naught that work. There's different ways to prove a lot of these by the different techniques of, I'll increase the negative or I'll drop this or not. There's different ways, and the different ways that you do them, you might get a different C and a different n naught. But as I have to show is that they exist. There exists. Are you with me on that? Okay. So how did we do this? How did
n cubed minus 5n is greater than or equal to.
Yeah, we just put this in here and then work it through, and then this is called a construction proof. We'll construct C being 0.5. So it's n cubed minus 5n is greater than or equal to 0.5 n cubed. But look, is greater than or equal to 0.5 n cubed. But look, what is the, oh well, here it is. Why am I doing it on the board? Greater than or equal to 0.5 n cubed. So, what is this? What are the steps? N cubed. So now what do we do to both sides? Or sorry, not to both sides, but do what? Take the 0.5 to the left, and the minus 5 to the right, and there's our finessing the negative sign, right? So 0.5 n cubed is greater than or equal to 5n, and now multiply both sides by what?
Put it back. 2.
By 2, and divide both sides by n, and what do we get? N squared greater than or equal to 10, so n is the positive root of 10. Remember that? So that's that technique. And so now we have identified the c is the 0.5 because it's a constant times n cubed is what we wanted. And then as long as n is greater than or equal to the square root of 10. So that's our n naught is the square root of 10. Okay, are we good? Remember that? So that was nice. So c is 0.5 and not the square root of 10. And then definition of tight bound. Big theta means what? Both what and what?
Big O and big O.
Yeah, that was a theorem. Is big O and big omega. Okay, so that was a nice review. Now, other part of the theory was recursive algorithms. And remember, there were writing recurrences. Okay, so you remember how to write a recurrence? So here, let's write, well here, let's do, let's write this recurrence, factorial n. If n is less than or equal to 0, then return 1, else return n times factorial n minus 1. So what is this? Let's do it in big theta notation. I think when we were first introducing this, we didn't use big theta right at the very beginning, but yeah, so what is a recurrence? It's t what?
T of n.
T of n, and it always has what shape? The brace and the base case and the recurrence. So what's this going to be? The base is going to be what? Big theta of 1. And the recurrence is going to be what? How long does it take to do, if it takes t of n to do n, how long does it take to do n minus 1? T of n minus 1. So what will this one be?
So T of n minus 1.
Well, yeah, big theta, yeah. And now when we were first doing this, we said 2 and then t of n minus 1 plus 3.
So that would have been like plus big theta.
And that was, yeah, but then we graduated to doing it like this.
Okay.
Right? Remember that? And then we did, here's one for binary. Oh, how about this binary search one? Remember the binary search? What's the?
N over 2?
Yeah, it does a.
Oh, okay.
Yeah. Well, how did this one work?
So the base case is big theta.
Big theta of 1.
And then how the binary search is, it breaks things up into like halves. So
Right.
it'd be.
And it either does that one or that one. It doesn't do both because it's if, else if. Right? So that does one, but each one of those is a what? How long does each one of those take? T of n over 2 because it's a binary. So what is it? T of n, so what is it? Big theta of 1 plus, or if n is less than or equal to 1, and t of n over 2 plus big theta of 1 if n is greater than 1.
And then if it did like both of the searches, it'd be 2.
Yes, if it did both, yeah. It would be 2 times that. And then towers. Now, now here is we talked about backward substitution. We've talked about the recurrence tree method. This is the one that you have to do. This is the one you have to know. we talked about the back substitution, the recurrence tree method, and then we also talked about the master theorem. Remember that? It's a cookbook for certain forms. Remember that? But anyway, the one that's more general is the guess and verify. So now, how do you set this up? This is an important piece of theory. How do you prove, so given a recurrence, how do you prove that a proposed solution is the solution to that recurrence? It's by induction, is right. It's by induction. So how would you do this? It's like, this is how you like back substitute, this is like how when you solve a system of equations, like 3 equations and 3 unknowns, and you get your answer, and what do? You go back and you check to make sure. This is how you go back and check to make sure that to verify that this is a solution. So how can we prove that T of n equals 2n plus 1 is a solution to that? So how do you set this up? It's by induction. So how do you do this? How do you do the base case?
So you start with
You start with
the proof.
with that, and you plug in the base case.
Right.
So
Base case n equals-
yes, so proof, base case. T of n equals 2 to the n minus 1. And then this equals by the base case. And how do we know what the base case is up there? It's if n equals 1. So then you put 1 in. And then what do you do? T of 1 by the what? By the definition of T of n.
Right.
Okay. So T of 1 is, by the definition of T of n, is 1 equals 1. So that one's done. The base case is done, right?
When you say like definition T, it's referring to that specific T.
Yes, it is that specific one, yeah. Are we good? But now how do we do the induction one? How do you set up the induction, how do you set up the inductive case?
Oh, prove that T of n plus 1 is equal to 2 to the n plus 1. Assuming.
Yeah, prove what, assuming what as the inductive hypothesis. Because we're trying to prove, what are we trying to prove? T of n equals 2 to the n minus 1. So yeah, so now actually there's 2 ways to do this. You could prove T of n plus 1 is 2 to the n plus 1 minus 1, assuming what? T of n is 2 to the n minus 1 as the inductive hypothesis. Or you could prove what? T of n equals 2 to the n minus 1, assuming what? T of n minus 1 equals to the n minus 1 minus 1 as the inductive hypothesis. And I think, I guess we're doing it the first way. So prove T of n plus 1 equals 2 to the n plus 1 minus 1, assuming what?
T of n equals 2
To the n minus 1 as the inductive hypothesis.
And then for the cases where it's like the binary search where it doesn't.
Where it doesn't have, then
It's T of n, or it's like T.
it's one, we'll do an example. Okay, so we're starting with what we're trying to prove, right? I mean, now we know what we're trying to prove, so what should we start with?
Plus 1.
I think we should start with T of n plus 1. All right? And then try to get it to equal what? 2 to the n plus 1 minus 1. So T of n plus 1 is what? Definition of T of n, but then replaced by n plus 1. So what is that? 2t of n plus 1 minus 1 plus 1. All right, that's from the definition. Are you with me? And then a little math is 2t to the n. But now that we have it in terms of t to the n, we can use our what? Inductive hypothesis. So that's inductive hypothesis, blah, blah, blah. We do some math, and we get it down to what? 2 to the n plus 1 minus 1, which is what we were trying to prove. Remember that? And now these are all on the slides. I don't want to. Here's another one with n over 2. Yeah, let's do this one. So now, what's the base case here? Well, we write down T of n equals log n plus 1, right? So T of n is log n plus 1. And the base case is
So the T T of 1 equals log 1 plus 1.
Yes, and by some math, that's,
The definition of T of n.
and then by definition of T of n, 1 equals 1.
Equals 1.
Okay? And now how about the inductive case? Prove what? No, now here's where we set, here's where you're,
Prove T of n is equal to log n plus 1,
Yeah.
assuming n minus 1 is equal
no, yeah, and that's incorrect. Because now what happens is the recurrence is dividing by 2. Remember how that worked?
Right.
So if the recurrence is dividing by 2, we don't prove exactly the same thing anymore. We prove what? T of what? 2n equals what?
Log n.
Log, no.
Oh,
P,
log 2
T
plus
of
1.
log 2n plus 1,
Yeah.
assuming what? Here, so that's T of 2n equals log 2n plus 1, assuming what?
T of n equals log n plus 1.
T of n equals log n plus 1 as the inductive hypothesis. Again. And so you start with T of 2n, definition of T of n, with n replaced by 2n, T of n plus 2, blah, blah, math, T of n plus 1, inductive hypothesis, log n plus 1 equals by some math, log n plus log, you had this little log stuff,
right.
remember that? And then that's how you do that. Now, and you know these orders, right? You know which is bigger. Which is bigger, n squared or n log n?
n squared.
N squared is bigger than n log n because log n is between 1 and n. Yeah, so anyway, those are the asymptotic orders. I assume we all know those. Now, do you remember this? Because this is, here, this is the performance, because this is, you asked theory of the material since the previous test. This was since the previous test.
Okay.
All right, so this is the performance of the LLRBTree. Do you remember this theorem? This is a very well-known theorem in, now I'm not in data structure, in the data structure literature. Now, I'm not going to ask you to be able to reproduce this whole thing. Okay, so it's pretty detailed. But I mean, maybe at one step, you know, but even that's not a guarantee. But anyway, you might want to review it. So now, do you remember this quantity that we defined? Okay, so first we have a lemma. Now, remember what this lemma, do you remember talking about this lemma? What is there about a red-black tree that makes it balanced, makes it not have really long stuff hanging off? The longest one can't be so long. I mean, what's the relationship between the longest and the shortest path from a root to a leaf? Double. The longest one can't be more than double the shortest one. And you can see that here. You can see why that is. That's because the shortest one has blacks all the way down, and the longest one has as many reds all the way down as possible. But what's the limit on the reds? You can't have two what?
Reds.
Two reds in a row. So do you see why that is? I mean, so do you see? So the shortest one, so the longest one has to be. So in a red-black tree of height h rooted at h, the black height of x is greater than or equal to h over 2. You can't have a longer. You can't have a path from the root to the node longer than twice the shortest one. And the shortest one is the black height, right? The shortest one is the black height. It's blacks all the way down. Okay? And do you remember this nx comma h? What was this nx comma h? That's the number of internal nodes in a red-black tree of height h rooted at node x. Remember that? Remember when we?
Yeah, I do.
Vaguely? Okay, so tell me, what is here? Let's do some examples. What is n 60, comma 6? Is the number of internal nodes. So 60, if we take a look at 60, it's the number of internal nodes in a tree of height h. So what is the height of the 60? It's 6 here. Do you see why?
So it's like the entire.
And it's how many internal nodes, so not including the nils. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
And you count 6.
And you count 60, yeah. And what is n 20, comma 4? See, 20 has a height of 4, right? 1, 2, no, wait. Is that right?
Yeah, I think so.
Oh, yeah, that's right. 1, 2, yeah, because we count the root.
Yeah.
1, 2, 3, 4, right. So n 20, comma 4 is 7. So 1, 2, 3, 4, 5, 6, 7. Remember that? That's that quantity.
How is it a height of 4?
Because it's the 20 is at one level, the 10 and the 35 are at the second level, the 5, the 15, and the 25 are at the third level, and the 12 is at the fourth level.
Oh, okay, okay.
Are you with me? And then we had this lemma 2, that n of x comma h is greater than or equal to 2 to the back height of h minus 1. This is the key to the performance analysis. Because what does this relate? What is n? N is the number of nodes. Are you with me? And what is the black height? That's the height of the tree. And it's the height of the tree that determines the performance, because it's a search tree, and when you go down, it's the height of the tree is how many comparisons you have to make to get to either doing an insert or a delete or contains. Are you with me? You see how that theory works? And so so the proof is by mathematical induction on the height of the tree. So here's the base case. N of x comma h is to the black height of x minus 1. Take the base case that the root is nil. And so that's the black height of nil. But with the root of nil, there are no internal nodes, so it's 0 to the black height of nil. With the root of nil, the black height is 0. So boom, boom, boom. That's true. No. I would get, no, I'm not, you don't need to memorize don't spend your time memorizing this proof. This is it's not fundamental. I mean, it's pretty basic and pretty standard, and it's all well known, but it doesn't have the importance that, oh, by the way, I'm also not going to ask you to do that one that you did have to prove. Do you remember what you had to prove?
Yeah.
What was it? What was the one that you did have to prove? You should at least know what that one is by now. So you proved it once. Now, do you know what it is? What's the any what?
Oh, sort.
Any sort algorithm that's based on what?
Pairwise comparison.
Pairwise comparisons is what?
Big theta element.
No, not big theta.
Big omega.
It's big omega. It's bounded below by what?
And LGN.
N log n. That means you can't do better. No matter how hard you try, you can't do better. Yeah, and that is really fundamental importance. Because you see why it's more important? Because that one is about what? That's a statement about what? All possible sort algorithms that are based on pairwise comparison. This is just a what? One particular red-black tree data structure. You see what I'm saying? But anyway. So no, just read through this. Make sure you understand it. Understand the definition. But don't spend a whole lot of time. I'm just asking that you be familiar with this. So you remember this?
Yeah.
So the link from X to child C is red. Then the black height of C is the black height of X. But if the link from X to child C is black, then the black height of C is the black height of X minus 1, because that one black link counts towards the black height. And then the other thing we said was that the minimum number of nodes in a tree rooted at X implies that both children have the minimum, implies that the links from X to both are black. And then we went through this. What did we discover? What did this analysis tell us? Our analysis told us that what? That H, for a red-black tree, H is less than or equal to what? 2 times the log of what? N plus 1. Which means, but that is big theta of what?
Log n.
Yes, that is big theta of log n. Do you realize what that means? That means that you can insert in time log n, because remember the insertion is just down and then fix up. And also you can remove in time big theta of log n. That's just down and fix up. You see what we're saying? So that's it. That's pretty remarkable. Do you realize that maybe we didn't emphasize this enough when we were doing this. Do you realize that what we have then is we have a data structure where the insertions and the deletions and the contains are all what? All three of them are what? Log base, big theta of log n. That's pretty cool. You see what we're saying? And then we compared this with the height balanced AVL trees. Also log n. All these balanced binary trees are all log n. But look, it's 1.44. So the constant is smaller. So it has, for doing contains, it's big theta of log n, but it's faster. But to keep it balanced, to do insertions and removals, it's the other way around. See? Yeah. Because it's more balanced than a red-black tree, and so it's harder to keep it. It takes more time to keep it more balanced. See, which makes sense.
Right.
You spend more time keeping it balanced than better balanced anyway. All right. Well, I think that was all I was going to do for the review for the theory. When is our final?
Wednesday.
Wednesday at,
1:30.
yeah.
I think it's 1:30.
Oh, one more thing I wanted to emphasize. I sent emails out to everybody, but please, I have not had time to emphasize this. But course evaluations are mandatory, so please send me your proof of, yeah, send me a screenshot. Yeah. All right, well, it's been great. Another great semester of data structures.
So this is
See you next year.